and welcome to my presentation. The Pico balloons thing has sort of taken a real interest in my life, not just sending up the balloon itself, but sort of all the electronics that go along with it. And of course, you can program your own tracker, the stuff you put in that actually gets sent up. And that's what's been keeping me very busy lately, because I'm sort of planning on all sorts of clever telemetry. Well, I think so anyway, in the future. So what we're going to do is I'll show a typical balloon setup and the hardware and a launch just for the fun of it. But then we're going to dive straight into the telemetry, because I mean, that's the interesting part of actually sending some scientific information from up there and receiving it down here on Earth. And well, besides just seeing where your balloon is, also seeing what's going on up there. So that's the agenda that we have up on the screen there. So this is a typical payload that I use, where you can see the solar panels, and in the middle there is a Raspberry Pi Pico, the smallest Raspberry Pi they make, with a board called the Jet pack, which provides a transmitter, which is actually just a frequency synthesizer, and a GPS module. And you can just see there at the bottom is the 5 centimeter GPS antenna. Now this is just in a test mode before I actually send it up. So here's one of the HF parts of the antenna, and there's the other half. So it's quite a thick wire, but in practice, when we actually launch it, it's only using 36 gauge enameled wire to keep everything light. But this is just in my test mode. So this is a balloon. Typically, you start by blowing it up to highish pressure just to get all the wrinkles out and stretch it a bit and make sure that there are no leaks. And then I leave it inflated like this for a day or two, as you can see dangling there on the left in my lounge, until we're happy, and then deflate it, and it'll be inflated with helium. I only use helium. It's easy. You can just go to Checkers and get them to fill your balloon. Or when I say fill, it's not filled. It's actually only about a quarter filled, because of course, due to Boyle's law and that, it expands as it goes up. So you've got to carefully work out how much to put in so it won't burst on the way up until it reaches the desired float altitude. And of course, the typical payload is the Whisper beacon, as we've already mentioned a few times. And most people are 20 meters, although I've homed in on 10 meters, because then you need a shorter antenna, of course, if you're using a halfway dipole. Much simpler than trying to launch a 10 meter length of very fine copper wire. So besides the Whisper beacon, as you might know, we do send additional telemetry like altitude, temperature, etc. But that is what we're going to get into soon and find out how do we actually do that, because Whisper, of course, only sends 3 things, and that is your call sign, your grid, and the power level. One other point is, in mine and a lot of people's, there's no battery, so it'll only transmit when it's in sunlight. And furthermore, the sunlight's got to be about greater than 20 degrees incidence on the panels, otherwise it won't have enough voltage to transmit. So here you can see a little bit more detail. I mentioned the Whisper beacon is constructed with a Raspberry Pi Pico, and we solder onto the back of it this Traquita jetpack board, which provides 3 things: the GPS, the radio transmitter with a 0.5 parts per million temperature controlled crystal oscillator, so we need it to be very stable, and a voltage monitor. So we only power on the Pico Pi when the voltage is above a threshold, because otherwise, if it was just simply connected to the solar panels, it could get into an unstable situation, and the Pi likes it to be fairly stable, or above a certain voltage anyway. So that's quite a key part as well. So the beacon, of course, requires an HF antenna, and an efficient one is a halfway dipole. So for 10 meters, as I said earlier, which is a nice short one, and in WSPR it's 28.1246 megahertz, you only need 5.07 meters in total. So the idea is you take half of it, it's a vertical dipole, so the top half is connected to the balloon, and then in the middle at the feed point you put your payload, and then dangling below is the other half of the half-wave dipole, as you can see on the right there. Right, I'm going to show you a short little video of the launch, a typical launch sequence. Okay, I hope you spotted the payload dangling in the middle towards the end there. Wasn't the greatest of videos, but anyway, I think you got the idea. Right, so WSPR beacon and spotting. So WSPR was developed by, as everyone knows, Joe Taylor, K1JT, and is a great way to monitor your balloon, as there are tens of thousands of amateurs out there, of course, which have automatic WSPR receivers listening 24/7. And each time a valid WSPR message is successfully decoded, it is uploaded to the usual WSPR website. So even if I can't receive my own balloon signals or my friends, it doesn't matter because the data is picked up by people all over the world and uploaded to the WSPR database. And as you can see on the right, this is from WSPR.rocks website, which is just a WSPR website, and there it's showing the red dots, the sort of the progress of the balloon as it was moving towards Australia, and the white dots are the people receiving it at that time. So without doing anything, you have a method of tracking your balloon, but we want more than that as radio amateurs, as we know. But now not all balloons use WSPR as a means for telemetry. Some use APRS, which of course will give you the position, or even LoRa, or combinations. So you could have WSPR to tell you where the balloon is, and where it is going, and then use LoRa to dump the data down when it gets within range of a receiver. So you could have a few friends around the world with LoRa receivers and pick it up that way. But still not such a good way to do it. So why use WSPR as a basis? Well, as I've mentioned already, it's widely received by many people, so we don't have to reinvent the wheel there. And of course, the key thing about WSPR is extremely sensitive. It can hear down to minus 28 dBs in the noise. So you don't need a strong transmitter either. And typically we transmit at 20 milliwatts. Yep, just 20 milliwatts. So this definitely indicates WSPR is the right approach. But as I said earlier, it doesn't contain any telemetry and it doesn't allow for that. It's just your call sign, the grid square where you are, and the power. So earlier on, some years back, Andy from Australia, he decided to pioneer a better way to send telemetry using JT9, which is also part of the WSPR JTX suite developed by Joe Taylor. And this allowed for global reception with only milliwatts of transmit, which is just, of course, what we want. However, for this telemetry to work, which he modified JT9, he had to have a custom version of WJS JTX, which again involved sending this or emailing it to people around the world who would be prepared to listen for your transmissions. So again, not ideal. You'd have to get volunteers to sit and listen with the specialized software. Then came along Hans Summers from QRP Labs, Golf 0 UPL. So he thought, no, there's a better way to do this. What about using the whisper-like packets and encoding the telemetry into a whisper-like packet? Then, of course, all the global existing network of whisper monitors could pick this up without any change to the software. So how do we do that? Well, the idea is to encode it into genuine call signs and grid square and that, so that it looks like a whisper message. In fact, it's encoded telemetry. So going through that in a bit more detail, as I mentioned before, a whisper transmission has 3 fields: 6-character call sign, which is 28 bits, a 4-character maidenhead grid square, which is 15 bits, and the power level, which is 7 bits. These 4 fields combine to form a 50-bit message. The 50-bit message is convolutionally encoded at a rate of half, K32, interleaved and combined with a synchronization vector to produce 162 symbols, which are transmitted using 4SK, which is a 4-tone frequency shift keying, at a symbol rate of 1.4648 baud. So the total transmission then would be 110.6 seconds, using about 6 hertz of bandwidth. Well, that's all standard. That is typical whisper. I just thought I'd throw in that. Right, so continuing with Hans's idea, he saw the balloon as sending a standard whisper message as usual, which of course would tell you whose balloon it is because it's got the call sign and a grid fall location, so you'd know where it is. But then his proposed repurposed whisper packet containing the encoded telemetry would be sent immediately after the whisper packet. And that is, in every 10-minute cycle, the first 2 minutes would be a standard whisper packet, followed directly afterwards with a 2-minute telemetry packet, a total of 4 minutes. But now, of course, if you're sending these whisper packets and the telemetry packets, you must have a way to link them, because hundreds of people could be sending all of these telemetry packets, and how would you know which telemetry packet belonged to who? Because if we've decided to use the call sign for telemetry, of course you won't know who it belongs to. So the idea of a channel number was devised. So this again is Hans Summers. He thought of 600 channels, 0 to 599. And this channel number is then encoded into 3 aspects of the telemetry packet. Firstly, using the call sign's first and third characters, and then it'll also determine the even numbered minute slot within the 10-minute cycle. So if you're a certain channel, you must only transmit like in the 4th minute, etc. I'll show you the table in a minute. And then finally, the third aspect to distinguish your telemetry from others is the so-called lane, which is the specific frequency within the 200 hertz whisper bandwidth to transmit in. So a bit more detail. So part of the channel number, which is encoded into the telemetry call sign's first and third characters, is he decided on the first character being a 0, 1, or Q, because this doesn't result in a valid call sign, an amateur radio's call sign, but it is accepted by whisper receivers. It's blind. It feels this is the correct format, so it'll accept it. And the third character is 0 to 9. Then part of the channel number, which determines the lane in which the tracker should transmit, is 4 lanes, which have been specified and correspond to 1 to 4 of the frequencies of the whisper band. As I've said, the whisper band is 200 hertz and is divided into 4 lanes. And here are the 4 frequencies for 10-meter band. As you can see them, they're all 28.126.020, etc. And then the even numbered minute slot within the 10-minute cycle of which to start transmitting. So here is a table, a channel map that's provided by Traquita's website. And as I said, 600 channels. for each whisper band. So you choose the band you want to be in. So each band can have its own 600 channels. And of course, you reserve this by call sign. You would log in with your call sign and reserve a particular channel. So here's an example. This is my call sign, and I've selected channel 463 in the 10-meter band and identified by that arrow. And in the column header, you'll see it shows Q3. So now you know that's the first and third characters to use in your call sign. Towards the right, it shows the minute, and it's got 0 in blue there. That means the sequence must start in the 0th minute of the 10-minute cycle. And then the lane is 1, and I said 4 lanes, so I'm in lane 1, and the frequency must be 28,126,020. So this would allow, as you can see, 600 people to be transmitting at the same time in the 10-meter band, as long as they follow this channel layout. And we could still decode and match up the telemetry packet with the original whisper packet, so we know who's sending it. So using this technique, I just want to show you typically what you would see in your whisper database. So here is the primary whisper packet sent at, you see the 0th minute of 10 minutes, ZR6WT, which is my call sign, and then followed by 3 telemetry packets. And you see they all have the Q and the 3 in the third spot. That's the only part that's required to make it unique. The rest of the digits, that and the grid NQ20, bears no resemblance to real call signs and grid squares, as I said, nor the power level, which is at the end here. All of that is the encoded telemetry. But to whisper receivers, they just see this as normal to whisper packets, receive it, and upload it to the whisper database. Right, so now how are we going to actually interpret this? I mean, so we got this going. Well, there are a number of websites that will decode it automatically for us. So I've mentioned a few here. There's the traquita.getup.io, whispertv.com, which is a very new one. It was only started around about, I think, June last year. And then there's the lu7aa.org. And of course, QRP-Labs has one as well. But that's a little bit more specialized. I tend to just stick with Traquita and Whisper TV. So it uses this channel information and your call sign, and it will match up the telemetry to your Whisper message. And I'm going to show you samples of that in a moment. But first, let me just tell you what Hans decided to send in the standard telemetry. So he, of course, he carefully devised this so that it would fit into one whisper packet, which is 50 bits. So the first part is a locator 56. And what that is to give us more resolution for the location on Earth. So the standard whisper is only 4 characters, as we know, but this adds a further 2 characters. So, for example, the GA part from Kilo Golf 16 Kilo Golf. And then the other nice things to know is the altitude, the temperature, voltage, speed. He also included this flag GPS valid, because sometimes you might not actually have a valid GPS lock, but you still want to send the packet and say, well, this was, like maybe the temperature is still valid, even if the locator is not valid. So that's an indication of whether this packet is valid or not. And then, as you'll see later, we are going to extend the telemetry. So there's 1 bit to say whether this is a standard telemetry, which is very fixed, which is what was developed by Hans Summers, or if it's non-standard, so it will be set to 0, and then other people can do what they like and come up with their non-standard telemetry. And you'd be able to distinguish between the two. Right, so how do we encode this telemetry? Well, real-world measurements, temperature, voltage, pressure, etc., are continuous or high resolution. So as is well known, this must be mapped to bounded integer ranges. i.e. normalized and quantized. Selecting suitable step sizes leads to the following bit usages. So locator 5.6, there's 2 characters which can be A to X. So that means there's 24 combinations of each. So 24 times 24 is 576 values, or 9.2 bits. Hans also decided on these others, altitude 0 to 21,000 meters in steps of 20, temperature minus 50, because it is often around the minus 30 to 40 up there, where these balloons typically fly, to 39C, which of course is when it launches. It can be 20 or 30 degrees at launch time. And that's in steps of 1. The voltage, this is the voltage as measured from the at the solar panel connection, which is 3 to 4.95 volts, steps of 50. And finally, the speed in knots, 0 to 82. So of course, once it's been mapped to a bounded integer, something like voltage is stored as 0 to 39, and we'll interpret it once it's decoded down on Earth. So how do we actually pack this into the WSPR message? Well, one approach would be packing the fields next to each other. But of course, locator 5.6 is a 9.2-bit field, and this would then require 10 bits, because you can't have 0.2 of a bit when you're packing next to each other. But there's a much better way to do this, and this is called mixed radix packing. The radix refers to the quantizations of the various telemetry components. All the telemetry fields are encoded using this mixed radix packing into a single large number, which we call the big number. Then we use mixed radix unpacking of this large number into the 3 WSPR fields, each having their own and different quantization to the telemetry fields. So for those who might not have heard of this mixed radix packing technique, I'm just going to show a simple example of how it works, and then we'll move into a bit more detail about our actual telemetry. So we'll take the example of 3 fields, V1, V2, V3. The first one has a size of 5, and what I mean by that is it's a radix 5 or 50 different values, or quantization of 50, meaning it's got 50 different values. V2 20 and V3 80. So of course I've purposely made this different to demonstrate the technique. So to store this efficiently, you would need the 3 of the radixes multiplied together, which gives you 80,000 distinct values to encode these 3 variables into a big number. And if you take log 2 of that, you'll see it's 16.28 bits. Now let's do it individually. If you took log 2, 50, 20, and 80, and you get those numbers there, and you add it up, you get 18 after rounding up to the nearest whole number. So clearly, it is more efficient to use this mixed radix packing technique. So let's actually go through a quick example. So as I said earlier, these are the sizes, 50, 20, and 80. And the example we're going to use is with V1 42, V2 17, and V3. This is the actual value. So the idea is you start with a big number, which is what you're trying to get to, set to 0. And you take its current value and multiply it by the quantization of the variable that you want to add in. So you're kind of shifting up all of the current items by that quantization. You add V3, and we start at the other end, V3, so that when you're decoding it, you get them back in the order you want, which is V1 to V3, in case anyone wonders why we're going backwards. So then the next line would be taking the current value of the big number, multiply by the variable 2's quantization, add V2, and so on. So the actual example there at the bottom, I'm taking, it starts at 0, of course, you multiply it by 80, which is the quantization of V3. You add in V3, which is 65, take that value, multiply it by the quantization of V2, which is 20, add 17, the value of V2, take that number, multiply it by 50, which is the quantization of V1, and add the V1 value, and you get a value of 65,892. And this guarantees reversible mapping. So decoding is the opposite, of course. So you start with a big number, and you would use mod arithmetic. So you take the modulus of the big number by the first variable's quantization. So in our case, it's 50. And if you've got a calculator handy and you take that number from the previous page, 65829, and do a mod on it of 50, you'll find 42, which is V1. Then you remove that part of the big number by doing an integer divide of the quantization for V1. So that's with the double slashes, integer divide. That result, you do a modulus of 20, and you'll get 17. And likewise, the third one, 65, which is what our original variables were. So right now we have this big number that we want to send as a WSPR packet. As I said, we're going to unpack this big number into 3 WSPR fields: call sign, grid, and power level, using the quantization of these fields. So what we effectively done is we've re-encoded our telemetry values into 3 other fields. And on the receiving end, we're going to recover it by first encoding the 3 WSPR fields into a big number and then decoding them using the quantization of the telemetry fields back. Sounds like quite a mouthful. But I'll show you a nice diagram just now. In practice, we don't just use one big number. There's some good reason to rather split it into 2. So the first big number will be encoded into the call sign, and the second big number will be encoded into the grid square and power level together. And there you'll see I've put the values possible. And I do a calculation here, taking the first telemetry fields that we're going to put into the big number, which is locator, 5, 6, and altitude. And we see that quantization results in 615168 values, which is less than the call sign quantization. So it'll fit nicely, and similar for the remaining telemetry fields: temperature, voltage, speed, GPS valid, and the telemetry type, which will go into the 4-character grid and power level. Right. So here, WSPR has 3 fields: the call sign, which we know is in the form of AAN XXX, where A is an alphanumeric, etc. However, C1 and C3, the first character of these, are already spoken for, as these have to be the fixed values for a particular channel in the band. In our early example, I used channel 463, and so this would give us a call sign looking like this: QX3XXX. So only the X's are the parts available for encoding the telemetry, where Q3 indicates which WSPR packet, well, it'll be used to connect this telemetry to the WSPR packet. All right, I'm giving you more detail there. C2 is the second character in the call sign. There's 36 possible values there. And C4 to 6 is A to Z, including blank if there are trailing characters. So you have quantization of 27 there. So hence a call sign space is 36 by 27 by 27, which can accommodate that many values. And grid, and grid 4 is the A to R, which is 18 values, and N, which is 10 values. And of course, there are 2 of each, as I've shown there. And the power level, there are 19 possible values. What is actually sent is discrete numbers 0, 3, 7, 10, etc. Hence, the grid and power level space will give you 18 squared because there's 2 at the start of the grid, and 10 squared because there's 2 followed by 2 numbers, plus the 19 possible values. So that can accommodate 615 values. So now why does this only give us 38.5 bits of the 50 bits that I'd mentioned earlier? Well, this comes down to the problem where we're fixing 2 characters in the call sign, C1 and C3. So that takes out quite a few values there. 9.8 bits are lost. And further, the 7 bits which we allocate to the power level, only 4.2 corresponding to the 19 values are available. The rest are used for whisper type internals to indicate whether it's a type 2 whisper packet, etc. So finally, we actually only have 38.5 bits usable. Right, so getting back to the real world example, where we try to encode the locator 56 and the altitude, I'm showing there the quantization values. Locator is 576, which is made up of 2 characters, both 24 because it's A to X only. And the altitude we had 1068. So using that earlier example, this is generalized. So you take the big number will become the locator 5 times 24 plus locator 6 times 1068, because there are remember, if you're encoding a particular value like altitude, you multiply your current big number by the quantization of the altitude, which is 1068. Right, so when we receive this whisper telemetry type packet, we have to reverse decode it or unpack it. And here is the format. C1 and C3 is fixed, so we don't decode that. We just start with C2, C4, 5, and 6. And again, we use this technique of modulus. So you start with the modulus of the first quantization of the character, which is 26, 26, and so on. And at each step, you remove that character that you've just decoded using modulus arithmetic by doing an integer divide by the quantization. So eventually, there you've got the 6 characters, and of course, the C1 and the C3 are the fixed characters that came from the channel mapping. Right, that's the similar one for grid 4 and power fields. I won't go into that detail. It's the same thing. I won't show that or that. All right, so here is a diagram which will explain, because it probably sounded a little convoluted and like what's really going on. So this really shows what's happening. We've got the telemetry values here, which we use multi-radix encoding into this big number. This is in the tracker itself, the payload. And then we use a multi-radix decode to get it into the 3 whisper fields, which is the call sign, the grid, and the power. This whisper message is transmitted, and at the receiving end, well, not at the whisper receiving end itself, but more the websites that will decode these whisper messages, we'll do a multi-radix encode of these 3 whisper fields into a big number, which should be the same one as before, and then we do the multi-radix decode back to the telemetry values. There's an example as shown before. So let's actually look at this telemetry, how it is decoded using some of these websites. So if we use whispertv.com and you enter in your call sign, the channel, and the band, it will read these WSPR packets and the telemetry and put them, well, connect them with each other and show you them on a map of the world. And if you put your cursor on a particular one, it gives you the detail, shows you the altitude, the speed at that point, the temperature, the voltage, and the sun's elevation, although that is calculated at your website. It also tells you how many people reported it, and I think this is the furthest distance away. And if you go into the data itself, I'll just go back. So here you'll see there's a little button where you can look at charts. You click on that, you'll then see all the telemetry lines and the WSPR. And if you click on one of these on the right, it'll show you the detail. So for this particular line, these are all the stations that picked it up. So ZS1 ERZ was transmitted, and these are the stations receiving it around the world, and followed by the telemetry packet. So you see it's got this encoded call sign with the channel number 01, and these are the guys that picked it up. And it's not necessarily that the person who picked up the WSPR packet also picked up the telemetry. As you see, PT2FHC doesn't occur down here. So he only picked up a WSPR message. He didn't pick up telemetry. Whereas VK1TZ, he picked up a WSPR message and the corresponding telemetry that went with it. Right, and further, these websites give you graphs, so you can see it in a graphical form. So if we look up here, this is the speed by date. This is 25 kilometers an hour, and there you see it goes up to 150 at times. And another useful website shows us all the balloons currently traveling the world. As you can see, very dense up north, not many down in the southern hemisphere, but there are a few. And here's one South African one, ZS1 AFB-1, that's flying just past South Africa. This was some time ago, though. Right, so just moving on a bit, extended telemetry. So the standard telemetry scheme that was designed by Hans Hammer is a fixed set of parameters encoded into a WSPR message. While effective, it has its limitation. The telemetry layout is hard-coded. Adding new sensors requires redesigning the encoding, and the web-based decoders would then have to understand the specific protocol variant. To solve this, extended telemetry was developed. It's a more flexible system for Pico balloon telemetries. Instead of defining fixed telemetry layout in the protocol, ET separates the system into two layers: the generic integer payload, the big number, and then an external schema which describes how to interpret it. The transmitted WSPR packet carries a single packed integer, as we know already, as for standard telemetry, and then the web decoder will use this associated schema to unpack that integer into real measurements. For this extended telemetry, they decided to actually add a more detailed header. Now, we already know about the telemetry type, which will indicate whether this is standard telemetry, or known as U4B, which was Hans's, or if it's a 0, that means it's extended, and then it can be anything you like. The other fields, reserved and type, are always 0, so it's kind of wasted space. But the header slot is useful because this says where is the telemetry going to be sent in respect to the starting WSPR packet. 0 is in fact where the WSPR packet is sent. So you shouldn't really be sending in 0 because that means there's no WSPR packet. You would normally only send 1, 2, or 3. And slot 1 is usually your U4B packet, which is the standard telemetry. But you don't have to send that. You can actually decide that that's not good enough and you want to send all your own extended telemetry and start in slot 1. Just laying that out a bit better. So slot 1 is your usual whisper packet. Slot 1 is the standard telemetry, and 2, 3, and 4 is available for non-standard. But as I said, you're not forced to do that. So here is a typical schema which was developed by Triqueta. So it looks like JSON. This one has 4 fields. So this was one of my examples where I'm sending the ambient temperature, which is different to what the Pico is measuring. So this is using a BM280. So I thought, this is sticking out from the Pico. So maybe it's not influenced by the Pico warming up. Anyway, just to compare the two, measure the humidity and pressure, and then that's all the BME 280 measures, but you can calculate the altitude given the pressure. So I send all 4 of these values across, and this is my schema to encode it. You see I give the minimum and maximum and the step size, because this will determine your quantization. In other words, how to encode it into that big number. Then if you go to Triqueta's website and you pass it the schema, this is the kind of data you get back. So here on the left, the yellow is the standard telemetry that comes with voltage, your altitude. It's got metric and imperial. You can switch off the imperial stuff. And then on the right, this is the telemetry encoded whisper message, and you see it's all these standard sort of 0 and 4, which just indicates the channel, and then there are the decoded values. The first one being ambient, which corresponds to that, and he appends the units to it, so that's what it looks like. So he's also saying that it occurred in slot 2, and that's its name, and there you get your values. So that's without changing any websites or whisper stuff. You can decode what you like once you've specified it in a schema, which is kind of JSON. The other website, whispertv.com, which I prefer, this is how it looks on that website. So you've got the originating, the grid that it was detected, and this is all your standard telemetry. And then here again, this is what it looks like using the whispertv.com website. And there he's showing the big number, the raw ET2, the raw extra telemetry that was found in slot 2. Right, so then Andy, who designed this whispertv.com website, decided to go one further and define what he calls generic ET, or later he decided to rather just call it custom telemetry, because the extended telemetry currently has quite a big header, and most of it is all 0, so it seems wasteful. So in his extended telemetry, he only wants to have header telemetry type, which is always going to be 0 because you are not sending standard telemetry, and of course the header slot. And then this gives you only 3.3 bits not used of your maximum of 38.5, which is very nice. So Andy, this is an example using his website where you can actually not hard code or manually code, I should say, a JSON schema. He's got a nice wizard here where you can say what kind of telemetry, the slot you want to send it in or decode it from, and then you give the names of them. You can give units, and again the start and end value and the step size. And that would then just generate the correct URL, which I'll show you an example of in the next slide, to decode it. So here is one of my other ones where I'm trying to send historical information. So which day did this happen, and which hour and minute, and what was the grid location at that time and altitude. Because one of the things that we find in Pico balloons is often they can go missing, in quotes, where no one receives them for days or weeks. And I thought, well, gee, you want to know what they probably were transmitting at that time, but just nobody received it. So I thought we should record telemetry on the local CMOS RAM and then send it later. So that's what I'm doing here. So I'm actually sending two telemetry packets, one in slot 2 and the other one in slot 3. And this is what it would look like decoding it on the whispertv.com. And so although there was a wizard to compile the URL, this is the URL that it generates. So you don't have to try and understand what all this means, but it's sort of like the position, which slot you're in. So there's slot 3, as you can see, and slot 2, there's slot 2. But that wizard makes it very easy. He goes even further. He allows filters. So if you've got too much data to send and you want to alternate between one kind of packet and another, you can put a field at the start of the packet, say whenever you like, in fact. So in this case here, I define a field called header type, which has two values, 0 or 1. If it's 0, you see this filter up here, I say decode it this way, which is my usual ambient humidity and pressure. But if I put a 1 in that, then it has a completely different meaning. And then I'm decoding a longitude and the 10-minute and grid 4 and so on. This is to do with my historical information where I was experimenting. So I can alternate between these two packets, all again without changing any websites or the Whisper protocol. All right, that's telemetry. I think we've had enough of that by now. Just a few other interesting things about Pico balloons. There are a few websites which you can use to predict the flight path. So, of course, the first one is to do with wind speeds and that. So, ventusky.com. So, if you look at that, you enter in, you've got the altitude that you want to look at. So, typically, these Pico balloons travel at about, or float, I should say, at about 12,000 meters. And here you can set the date and time, and you can see what's happening. And here's a scale to show the speed. So here, through the middle of Australia, was pretty high. It looks like it was about 130 to 140 kilometers an hour. And here it's much slower, about 60. So if you know your balloon is here presently, you can predict that it's going to go like that. Or if it's up there, you can see it's not going to go straight across. It's going to rather dip down like that. But now again, whispertv.com decided to build this in and make it automatic. So look at this. Here, I clicked on the last position there, and you click there and you select path prediction. And then this gray line is the predicted path. So it's taking all of this information into account, your altitude, your temperature, and the winds at that time, and also for the days in advance. And it'll show you where do you expect it to go. Which I thought was very nifty. That's something that's only just come about recently in the last month or so. Okay, so we said this is science in progress. So let's discuss a little bit of the science. So what makes a Pico balloon science remarkable is the cost to science ratio. For a few hundred rands in parts and a ham radio license, a hobbyist can generate months of genuine atmospheric data from the stratosphere, data that is publicly archived and can be used by researchers. The community is essentially building a distributed citizen-operated global sensor network, filling in gaps that the government weather station agencies simply cannot afford to cover. So firstly, we've got, of course, the atmospheric wind data. So you saw Ventusky shows what it's predicting. But now these Pico balloons can, with the standard GPS location and altitude, and wind speed and wind direction and associated error messages, this creates a continuous global picture of the upper troposphere and lower stratosphere wind patterns that is difficult and expensive to gather any other way. So you're kind of then validating what Ventusky has shown. Jet stream and weather pattern mapping, NOAA and HWPP WSPLIT, which is the hybrid split particle Lagrangian integrated trajectory model, is routinely used by balloon teams to project flight paths, and the actual observed flight data in turn validates or challenges these models. Real-world balloon tracks over remote oceans and polar regions are particularly valuable since weather balloons launched by meteorological services don't cover these areas consistently. And of course, radio propagation sounds. Every whisper transmission in itself is a data point for the ionospheric science. The network of ham radio receivers picking up these signals from thousands of kilometers away feeds into our understanding of how radio waves travel through the atmosphere. Data useful for telecommunications, space, weather research, and HF radio planning. Then we have polar and high altitude observations. Some Pico balloons venture into the polar regions, and during the June solstice can remain in continuous sunlight while reaching extreme latitudes deep inside the Arctic. These flights traverse some of the most data-sparse regions on Earth, and their primary contribution is tracking long-duration stratospheric air movement, with additional temperature, humidity, and pressure data depending on the onboard sensors. Long-duration platform experiments. Flights lasting many months allow study of electronics, reliability in the cold, of course, extreme cold, it gets down to -30, -40 there. Battery when used, degradation in stratospheric conditions, and solar panel aging. These conditions approximate aspects of near science environments. So a particular valuable contribution. Long duration Pico balloons are usually good at studying stratospheric circulation stability over months, because conventional weather balloons only last about 2 hours. This is a unique niche where amateur experiences can contribute meaningfully. But however, there are realistic limitations. Despite their value, Pico balloon measurements have important constraints. Sensor calibration is often poor. Payload orientation can introduce bias, e.g. solar heating effects. Altitude is not tightly controlled, and measurement standards are inconsistent. As a result, the data is best suited for trend observation and trajectory analysis rather than precision meteorology. Well, that's it. Sorry, I think it went on much longer than we expected. Hope you enjoyed it.